So this way things will be recorded. Cool. And yeah, I have to switch between the screens, and sometimes it gets confusing because I'm using OBS to capture this screen, and OBS is actually running on my other screen. So when I want to move the cursor over to that screen and go back and forth, I have to remember where the cursor really is, because it appears on this screen, but it's actually on the other side sometimes. And I need my reading glasses, because otherwise I cannot read this close. There we go. All right, so I'm not sure how many of you got time to just do this little exercise here. I hope at least some of you got a chance to do it, because this is really, it's just something I threw together in a few minutes, but it does test whether you kind of pay attention to the notation, the symbols, and also the technique of using a truth table. So in other words, it really helps to identify whether you understood the concepts that we talked about on Monday or not. But it's not a real assessment. If you say, I have no idea how to answer this question, hey, that's okay, because I'm going to answer that question now. So are we ready to kind of address this particular one? Okay. All right. So what I'll do is I am going to copy and paste this into my text editor. And this is from the morning class. I can just go ahead and get rid of that. And here is what we have here. So this is partially why I chose to use this notation, is because I can just type it on the keyboard. You just need a plain text editor like Notepad, to type all of these Boolean equation. You don't need a special editor with the wedge for the and, the b for the or, and then the not is like a cliff symbol. All right, so let's get to this one, and we'll try to see whether we understand what it is, what it's trying to express. All right, so I'm going to use a cursor under the text so that you can kind of know which part I'm paying attention to. All right, parentheses, we don't have to kind of explain. So what is this exclamation point doing here? What is it representing as a Boolean operator? Not. Very good. Okay, so it's Boolean or logical negation. What about this plus here? Now remember, the entire context is this is a Boolean expression. So x, y, and z are all Boolean, either true or false. So under that context, what is the plus representing? Or. Very good. Okay. And then over here, okay, between these two, the close and the open parentheses, what is it representing? There's no operator here. It's an and, because it is how we represent multiplication in normal algebra notation. But in Boolean algebra, it is representing conjunction, or what we know as and. Very good. What about this equal to and greater than? Equal, greater than. Which symbol does it resemble when we're dealing with Boolean operators? Implies. Very good. Okay, so if that's implies. And then finally, with this portion, without the parentheses, should I do the or y and then take the entire thing and then end it with not z? Or should I compute the conjunction of y and not z and then have that result to be ORed with the first part of the expression? In the second one, very good, because the priority of operators are the same when we are looking at the same kind of operator, even though it's in the Boolean expression. So multiplication takes place first, and then the addition takes place later. Okay, so the prioritization of the operators is still the same. All right, very good. So now we can move on to the second part of the question, which is to create a truth table for this particular expression. How many independent variables do we have in this expression? We got 3 independent variables, because we got x, we got y, and we also have z. So there are 3 independent variables. In this case, which means there are 3 columns dedicated to just the independent variables, x, y, z. All right. So how many rows do you think this truth table is going to have? 8 is good. 8 is correct. So how did we come to the number of 8 without even showing what is on each row? How did you figure out it's 8?
Wrote it out, all the possibilities.
Right?
But,
but why is it 8? It has something to do with 3 independent variables. Go ahead.
Is it 2 plus 8 3?
2 to the power of 3 is 8. That is correct. And when the variables are independent, we are basically just raising 2 to the power of the number of variables in this case. All right, very good. So I'm just going to go through the tedious part of giving you the values of the independent variables. And it's tedious. What I'm going to do, I'll just be lazy here because I hate typing the extra spaces when I don't really want to, because it makes it so much easier to type 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. There we go. Does it look like a binary number, like a sequence of binary numbers going from 0, 0, 0 all the way to 1, 1, 1? Yeah. Are you surprised? I hope not, because that's basically there's not really a whole lot of differences between a digit of a binary number versus a single Boolean variable, because you can call it 0 or 1, or you can call it false or true, so it doesn't make that much of a difference. All right. So now when it comes to actually populating the actual value of the expressions, do you expect me to actually do it manually? No. So what are we going to do? There are several ways to do this. You can use a spreadsheet to do it, okay? This is something that I talked about earlier in class for CISP440, but since in that class it's not so much focusing on Boolean logic, I did not actually show the class how to do it. All right, so we'll go ahead and compute the truth table using a spreadsheet. And we all have access to Google Sheets, right? So Google Sheets is a really good tool to use for this case, because once I'm done with it, I can share the link with you guys. So you guys don't have to busy copying everything, because I will give you the spreadsheet. So you'll have all the equations needed to get this done. So what I'll do is I'm going to go to the shared folder and create a new spreadsheet in the shared folder, which means it is going to be shared automatically. But right now, you can just kind of focus on the concept instead of trying to copy everything, because the whole lecture is getting recorded anyway. All right, so I am going to paste the equation as the name of the file. That makes it very easy to identify. All right, so the first thing is, how do we give the values of x, y, z, and populate the columns? Okay, that would be the first question. So I'm just going to say, okay, column A is going to be the value of x, column B is the value of y, and then column C is the value of z. There are a lot of tools, there are a lot of ways to do this. I could have done this manually and just retype everything, but that kind of defeats the whole purpose, right? But you also saw earlier that you saw binary numbers, right? So you saw 0, 0, 0, which represents the value of 0, all the way up to 1, 1, 1, which represents the value of, what is 1, 1, 1 in base 2 representing? If I want to, no, 7, 7, yep, because it is 1 plus 2 plus 4. You shifted the whole thing by, no, you forgot the 1, yep. That's okay. So now the next question is, Pat, don't you need a column so that we can at least start with a number from 0 to 7? The answer is no, because the row number is also sequential. So I can rely on the row numbers. But in a spreadsheet, you can get the row number of a particular cell using a formula called This is like a big, huge mystery thing. The formula that will give you the row number of a cell is row, just ROW row, okay? So now we say, okay, let me see the double check, right? This is how I write programs. I do it step by step because this way, if I do make a mistake, I know where I make the mistake and I can fix it. All right, so row is just 2. Okay, that looks fine. And if I drag it down to 9, I get 2 to 9. All right, so if I can get to 2 to 9, what is the next step to convert it to 0 to 7? Subtract 2 from it. Okay, very good. So that means if I just go back to this equation here and I say row minus 2, then I get the number that I need for that purpose. Okay, now I have the numbers 0 to 7. Very good. But x is not supposed to be 0 to 7. X is supposed to be what? 0, 0, 0, 0, and then 1, 1, 1, 1. So how do I get to that particular digit as a base 2 representation? So this is the moment where people who took CISP440 from me can say, oh, I remember exactly what equation we're supposed to use. Okay. But if you have not taken CISP440 from me, how do you extract bit 2 of a binary number if you're given the value already? In other words, how many 4s are we talking about? How do we get the number of 4s in a particular number?
5 by 4.
Hmm?
5 by 4. Divide by 4.
Divided by 4. Very good. Okay, so now we go like, cool. Let's do it. Division by 2. Division by 4. Okay. And kind of drag it down. Almost. Okay. Because the spreadsheet is not doing integer division, so it's giving you the actual answer. It's giving you 0.25, which is 1/4, 1/4, and then we have 1/2, 3/4, 1, and 1 and 1/4, and so on. So how do we convert that to just 0, 0, 0, 0, and then 1, 1, 1, 1? What is the name of that function to ignore the fractional part? Floor. Very good. Good job. So now we go back, but you can see how I construct this not with one single, expression because I just work on it gradually. So now we take the floor of the expression that we already have and cool. Right? That is nice. But and what about the next row, next column? The next column is supposed to be 0, 0, 1, 1, 0, 0, 1, 1, right? So what is changed between column A and column B? Instead of trying to extract what is in bit 2, we're trying to extract what is in bit 1. So what we used to divide by 4, now we need to divide by 2. But that's not going to solve the problem, because if you divide it by 2, I can tell right away. What is 6 divided by 2? It's 3. But wait, hold on a second here. I don't want a 3 here, because we want 3 mod 2. So after the division, we also want to do a mod 2. So after we take the floor of the quotient, we also want to do a mod 2 first. Okay. So what I really want to do is to basically come up with a way to specify this whole thing so that I don't have to individually come up with the values for the 3 columns. So now I say, okay, here's mod, and we are modding it with 2. Okay, we'll see whether it changes anything with this column. Okay, it didn't do a single thing because the largest value that we end up with here is just 1. 1 mod 2 is 1, so it didn't do anything to this particular column. All right, so let me go back to the first cell, and then we ask, okay, so what is preventing us to just copy this equation all the way up to here so that we can figure out all the values of y and z as well? Well, you look for the constants, right? Okay, in the equation, in the formula, the constants would be the issue. But the 2 is not the issue. So if you look at the minus 2, that is not an issue because it is an offset due to the configuration of the spreadsheet. So that minus 2 has to stay. No way to get rid of that minus 2. What about the other 2? That's base 2. So we cannot get rid of the mod 2 either. So now we have only one constant left, which is the 4. The 4 is not really that big of a deal because the 4 has to do with we are looking at bit 2. So if we look at bit 1, it would have been a 2. And if we were to look at bit 0, it would have been a 1. Okay? So in theory, I can just copy and paste and then just change the 4 to a 2 and then change the 4 to a 1, to get all the values that I need. In a normal case, that's actually going to take me less time than to completely generalize this expression. But as a computer science person, that's what drives me. Okay, can I come up with a universal expression so that it is the same expression across all 3 variables and I get it all done at the same time? So now the question is, how did I come up with the value of 4? Why is it bit 2? Well, that's because column C is bit 0. Column B is bit 1, and then column A is bit 2. So now you have to think about, okay, and 4 is 2 to the power of something that's relative to the positioning of the column. Is that okay? Maybe? Okay. So we are going to change this, and then we understand that this 4 here really should not be a constant. It is the power of 2 to something, and what we want to put into the blinky cursor here is basically saying if it's column A, it's going to be 2. If it's column B, it's going to be 1. And if it's column C, it's going to be 0. And can anyone guess what formula will return the column number of a cell? Column, very good. Okay, so we know that column is somewhere in here. So I'm just going to put it here. Okay, but it's not going to work like the way it is because column starts with 1 for one thing. So column A is actually going to have a numerical value of 1, and then numerical value of 2, and a numerical value of 3. No, that's not what we want because it doesn't even have the right offset because it's 1, 2, 3 instead of 2, 1, 0. So now I'm going to ask you guys, how do you convert the values of 1, 2, 3, the sequence, to 2, 1, 0 in algebra?
Subtract.
3 minus the column number. That would do it. Let's see, does it do it? Yes. Very good. So now we say this is just 3 minus the column number. And, okay, maybe I did a wrong number of arguments of mod. Okay, that means I forgot to close a parentheses somewhere. I think it's the power. Okay, let's see, match the parentheses. I think this one is, there we go. All right, so let's see. So normally, if I'm home, I would just kind of test it on the column first. But here, I just feel like I just have a unexplainable self-confidence and say, I think this is going to work. That's because, Hugh, contributed to the answer. If he is coming up with the answer, I can trust it. Oh, nope. Okay, never mind. There we go. Woohoo! But do you guys see how to do this? How to approach this problem? You have to do it one step at a time. So the first thing I did was to come up with a sequence of 0 to 7, and then I tried to figure out how do I isolate one particular bit if I were to look at the value as a binary, as a base 2 number, and then I tried to figure out, okay, so how do I generalize the 4, 2, 1, by using the positioning of the column. So it's a really step-by-step process. Okay, now, is this part of what CISP440 is supposed to teach? The answer is no. But is this going to be handy, for, not only this class, but for some of your other classes? I think so. I mean, this is not going to be the last class where you have to come up with a truth table or, you know, converting, a value into its binary form and be able to extract each individual digit. So, there we go. All right. So now we look at the equation, and then we just have to kind of code it in the or and the and stuff like that, with column D. And this is the tedious part. I actually wrote a parser. I wrote a parser that can parse the infix notation and crank out the prefix notation just because I had a need to do it. But I don't have the parser with me, so this time I actually have to do it by hand. All right, so the last operation of the entire expression is what? What was the last operation? No,
Not
no,
or.
or. Very good. Well, we only have 4 different operators here. We guessed the third one that we guessed was right. So we have an or. Okay, this is how I write programs. Some people look at this and go like, wait, why are you closing the parentheses? Because if I don't, I would have forgotten. Okay, so I write programs, from a structure perspective and not so much from, this is the starting point and I'm just going to write the code linearly. Okay, there's nothing linear about this. All right, so on the left-hand side of the or, what do we have? What is the last operation on the left-hand side of this outermost or? Phew, that was a mouthful. In other words, if you just focus on this part of the expression, what is the last operator? Is an and, very good. And then inside the and, we have 2 components, and the first one is also the result of an or. The second one is the result of an or as well, because there's no such thing as an implication, unfortunately, in the spreadsheet. So I will show you how to do a implication using just or and not, okay? And now we are ready to go back in and specify what are we oring here. So we have the not of x. Oh, okay. This part gets a little harder because I have to be able to control the cursor back to where I need to insert the second one, and the second one is y. There we go. And then the other or is the mysterious one, because I need to somehow express, what was it, y implies z. Y implies z is exactly the same thing as not y or z. Let me say that one more time. Y implies z is exactly the same thing as not y or z. Okay? So are you guys just going to write it down and say, oh, if text says it, it has to be right? No. Okay, good answer. So if the answer to that question is no, then what do you do to say, well, I really need to check whether tag told me the truth or not? How do you check? Okay. Sorry? Make a truth table. Very good. Okay, I like that. So now we go to the truth table. Well, this is the one that we're working on, so we'll ignore that for now. So we just focus on yz, and then we have y implies z. Then we also have not y or z, because that's what I claim to be the same as y implies z. With only 2 independent variables, we have 0, 1, 1, 0, 0, 0, 0, 1, 1, 0, and 1, 1. And this is going to be 1, 1, 0, 1. How did I come up with the third column, 1, 1, 0, 1? That's the definition. Very good. Okay. So that means, if someone looking at the third column is wondering, where is that coming from? That's probably a good indicator that you might need to review the content of the lecture a little more often. I said that not to criticize people, but to basically say, if you don't do that, and all of this stuff is starting to pile up, it's going to be really, really bad at a certain point. So it's very important to review the content of each lecture, especially if it is just definitions. Because definitions is nothing more than, oh, I know where to find it. Okay, it is somewhere in the text. So if you have your own notes, I would put all the definitions in one particular place, so it's easier for you to locate all the definitions. On the other hand, if you have the printed version of my notes, you can use a post-it. Okay, just have a little post-it, stick it right next to each definition. The idea is you want to make it easy to locate the definitions. Okay, but for something like this, it is also important to just memorize it. Okay, because it's just 4 individual bits. So now we look at the fourth column, and we ask, what if y is false and then z is also false? If y is false, not y is true. If one side of a disjunction is true, then the whole thing has to be true. So not have I only answered the question for the first row, but I have also just answered the question for the second row. Does that make sense? Because they both start with not y, and since for the first 2 rows y is false, not false is true, I only need one side of a disjunction to be true for the entire thing to be true. So that's why I can determine the values of the first 2 rows already, not a problem. For the third row, we have y being true, z being false. So not y is going to be false because y itself is true, but z is also false also. So now we have false or false, which means the entire thing is false. Very good.
Negative y, no, negative x и negative z, negative y, no.
Oh, we're just
no, one negative y,
okay.
x negative z.
Pretend that is not there. Pretend that we are only working with this portion. We're only working with this portion to understand why your y implies z is the same thing as not z or not y or z. That was the purpose of this truth table. We're only looking at y, z as independent variables, and the purpose is to show why y implies z is the same thing as not y or z. Okay? Yep. Oh, okay, you were just stretching? Okay. So good. And then the last one is going to be true, and this is the easy one to figure out too, because z is true, and it's one of the 2 components. We all good? But now we can look at these 2 columns. The last 2 columns, you can see how they are identical. Right? So now we have the proof. Okay, this is all you need to do to prove that 2 different expressions are equivalent when you're dealing with Boolean algebra. You wish you could do this to general algebra, right? Just kind of test out all the cases and use a table and say, yeah, these 2 are the same. Nope, you cannot do it if x, y, these variables are not Boolean because there's an infinite number of integers, so you can't really do it to integers. All right, so getting back, this is just one step of what we want to do. So getting back here, I am converting the implication into a OR. So we have to negate the left-hand side, which is also called the precedent. So we have a not, and that's going to be a y, which is a b2. And then the right-hand side is not negated in the OR. So that's just z, which is c2 in terms of self-reference. All right, so now we have handled in parentheses, not x or y, close paren, open paren again, y implies z. So that conjunction is now handled. So now this and is all done. The next component is going to be the right-hand side of the OR. Let me point out which OR we are dealing with. So we are trying to figure out what is y not z. All right, so I have to count parentheses. Fortunately, Google Sheet and any spreadsheet should do it these days is to match the parentheses. So if you're on one, either it's open or closed, it will basically highlight the other side, which helps a lot. Okay, so now we have the other side is a conjunction, so it's an and. And the two things that we're ANDing is y is 1, so b2 is 1, and then the negation of z is the other one, so we have not, z is c2, like so. And I think that's it. All right. So we have, so this is the truth table. And I just used, how long? About 20 minutes or so, to get this done. And some of you are going to say, but Tech, if you just do everything by hand, you would have done by, like 10 minutes ago. It's just a lot more tedious. But then I would not be a very good, software person, would I? Because as a software person, as a developer, as a software engineer, what is your task? Why are you hired and get a $200,000 job? What does your employer want you to do? Efficiency. Anything that can be automated should be automated. So I just figure out how to automate this. So in the future, I can now just say, hey, I have this script here and it can all be done. The only thing that is missing is the parser. In other words, I would like to do this conversion itself and do it in a program as well. Okay, let me re-emphasize what I mean by that. I want a program that would take this notation and crank out this notation here. Some of you, after you transition to a 4-year university, you might have the option to take a class called either compiler design, compiler theory, blah, 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 something like that. That class will teach you how to do this. How do you parse an infix notation, create the syntax tree, and then traverse the syntax tree, in this case, using I have to think about what order. This would be it's not an in-order traversal. This is going to be it's the depth first search. So using a depth first search, you would be able to generate the actual prefix notation from the infix notation. But that's in the future, okay? Hopefully you guys will have the opportunity to take that class because a compiler is interesting. To me, it's interesting. All right. So we have just gone through the exercise, the informal exercise that I presented on the other day. But in addition to explaining the concepts that we have encountered on Monday, I've also explained a bunch of other things that some of you are thinking, but this has nothing to do with CISP440. It does happen quite often in my classes. It doesn't matter which class it is. All right, so there are some other questions. There was one particular question about, can I summarize what CISP440 discrete structure is about? Because when you read the description of CISP440, it doesn't seem to connect with any of the other classes. It's kind of like a potpourri, right? It's kind of like a random mixture of topics. On one hand, we talk about logic, we talk about predicate calculus, we talk about propositional logic. On the other side, we talk about counting. I mean, do you guys know how to count?
Yes.
More or less, right? So it depends on what do you mean by counting. What is the total number of possible tickets, when you look at, Super Lotto? What are your chances of winning the jackpot? Don't you think those are kind of important math? Because if you drive by the billboard on the highway, you go like, wow, it's up to, let's say 20 million for the jackpot. So if you don't understand, the counting part, then you don't understand the probability of winning the jackpot. They go like, oh, maybe it's worth my dollar, to buy a ticket. No, it is not. Not even close. What if it is 300 million? That has got to be good. No. So that's the counting part, okay? So we got counting, we got logic, and then we also have probability, which is kind of related to that. But probability also has a different side to the way we talk about probability in 440. So it has to do with flipping a coin. Okay. So if you flip a coin and the coin is slightly loaded, let's say it's zero point 0.6 versus and zero point 0.4, in terms of the probability of landing on the head versus landing on the tail. So now I can ask you, what is the probability of you flipping the coin, let's say 5 times, and landing on the head 3 times? Okay, you will be able to compute that probability. So if you ever go to a casino and you're in a gambling situation, you can now kind of calculate the odds, or at least you can tell whether the coin is loaded or not. So you might say, but that's a really limited and kind of dubious application, right? Sounds dubious to me. If you're not going to a casino, why would I care about binary or binomial distribution? Well, think about sending a packet, okay, through Wi-Fi. Okay, if I can tell you that the chances of one bit being transmitted incorrectly is 0.01%. Okay, that's insanely high, but I'm just using it as an example. And you have a packet of 1,024 bits. So now I'm going to ask you, what are the chances that at least one bit out of the 1,024 bits is erroneous in the entire packet? Do you think that might be slightly related to computer science or networking? If you answer no to that question, then I'm going to say, okay, just try to play your League of Legends or whatever game that you play that has high stake, and there's a microwave between you and the router, the Wi-Fi router, and you're still using 2.5 gigahertz technology. After that experience, you can come back to me and say, Tech, I still don't think this stuff matters at all. Or you can say, man, that sucks. Stop using the microwave. You're messing up my game. And why is that the case? Because microwaves use about 2.4 gigahertz. That's the microwave frequency, which coincides, unfortunately, with 2.4 gigahertz, which is what older Wi-Fi routers tend to use. So the interference coming out of a microwave oven can really, really impact that error rate of the Wi-Fi setup. Bluetooth too, because Bluetooth is also based on 2.4 gigahertz. I know now we have 5 gigahertz band, and that's much better in terms of interference from microwave ovens. So there we go. There's always a reason for everything, right? Anything else? Oh, okay. That brings up to another question that I got, from students, and it has to do with how come only ARC has a co-requisite of 430? Well, as it turns out, I looked it up. Okay, all 4 colleges have different requirements to get into this class. FLC has the least, which is only CISP440. And no, I take it back because CRC is the same as us. Okay, 430 as a co-requisite, and then Sac City uses 400 and 401 as a prerequisite to this class. So it's not a co-requisite, but it's a prerequisite. So each college or each campus has its own specification of what is required to get into this class. Now, this is also a good time to mention articulation with 4-year universities can also be campus dependent. I have had a student who took this class from a sister campus, and it did not count for transfer purposes. So that would be a bad situation. I just want to make you guys aware of that situation. So when you want to take a class from a certain campus and your objective is to transfer to a particular university, you really have to make sure that it is okay to take that class from whatever campus you want to sign up, in that case, because the articulation agreements are not the same between campuses. Because if I didn't tell you, most of you may not know about it. You would think, oh, it's the same district, it has the same number, so they should all be the same, and that is not the case. All righty. Moving on. So let's see, where are we now? I am lost. And I can still get back to the main topic. All right, so bottom line is if you have not taken notes or organized in your notes to put all the definitions at one place and be familiar with those symbols and definitions right after class, you might want to consider just spending some time between class meetings so that you become familiarized with the concept of a previous class. I think it's really, really important in a class like this. And we are now going to start with basic set theory. And it's not even really set theory, it really is just notations. So we're going to start with a discussion of a set and its elements. The best way to look at a set and the elements contained in a set is not really to read my stuff because it's awfully dry. If I were a student in this class and I'm asked to read this dry stuff here, I would have fallen asleep. So the easiest way to look at it is a folder. A set is like a folder. A folder is what? It's just a container, right? And the files inside the folder are the elements. So now you can say, is this particular file in that folder? You can ask that question. It's either yes, it is in that folder, or no, it is not in that folder. So if a file is in a folder, then we say the corresponding file, if you see it as an element, it is an element of the set, which is the folder that is containing the file. So that's the quickest and easiest way to understand what is a set and what is an element. So in this analogy, once again, the set is the folder, and then the element is quote unquote the file. Are we good so far? So now the next item is, are there any restrictions? Can a set contain two elements that are identical? So that translates to the question of, if you have a folder, can you have two files of exactly the same file name in that folder? Okay, so I like all the answers of no, you cannot, but I can see how a Windows user would say, yeah, I've seen it all the time. But that's because, I think starting with Windows 7, I think, the default is it will hide the extension of a file. So if you have, let's say, setup.dll, setup.exe, setup.cfg, and setup.txt, then you end up with 4 files showing up as just setup in the folder. But in reality, the extension is a part of the file name, so those are 4 distinct files with distinct names. It's the same thing with a set. A set can only contain a value up to once. It may not contain it, but if it does, it can only happen once. Are we good so far? And since I'm using folders and files, I'm hoping some of you in your mind is already extending that argument and say, can we have a set that contains another set as its element? The answer is also yes. So you can actually have nested containment of elements. So you can have a set that contains another set as its own element, and so on. Are we good so far? Next one. Is there an inherent ordering of elements within a set? The answer is no. Okay, so there's no specific ordering of things or elements within a set. So that's kind of important. Now, if you think about files in a folder, it depends on how you want to sort it, right? Because you can sort it by last modification time. That's one way. Alphabetical order in a non-decreasing order. That's another way. Alphabetical order in reverse order. Okay, in reverse alphabetical order. That's another way. So you have different ways of sorting because if you need to know what is in a particular folder, your computer has to give you a quote unquote list in a particular order, so you can specify the order. But there's no inherent ordering within the files in the folder. There's no inherent ordering. Are we doing okay so far? Okay. So now we can go ahead and present a few examples. There are a few examples in the notes already. If you have read the notes ahead of time, it's already there. But I'm going to go through a few examples here, like this T over here. This one is not too big of a deal because we can type this basically verbatim using a plain text editor. So I'm not going to say anything. So in this notation here, T is the name of the set. And then the curly braces are very important because those are the delimiters. They basically state this is the beginning and this is the end of the content of a specific set. So in this case, we have the content of 12, 5, 2.2, 7, -1, and 10. So how many elements are in this set T? 1, 2, 3, 4, 5, 6. So there's 6 elements in this particular set. Are we good so far? So remember, the curly braces are important because it is a way for us to differentiate where is the starting point and where is the end of the list of elements in a set. All right, cool. Now we are going to look at the first symbol that is not unusual. Okay, this is not something that you see every day. See this thing that looks like an uppercase E, but it's not? It is called element of. Okay, so this little symbol is called element of, otherwise also known as in, just in. So you can say 2.2 is an element of T, or you can say 2.2 is in T. So both of those are common ways to refer to what this means. But it is not an assertion. In other words, it is not telling you that 2.2 is in the set T. It is more like a question. In other words, it is a Boolean expression. It's either true or false. In this case, because of the way I define T, 2.2 is in T is true. It is a Boolean expression. But if you look at the other expression down here, 23 is an element of T, is false. It is a Boolean expression. It has 2 possibilities. It's either true or false. So are we doing okay so far with this particular paragraph? Okay. And then the next question is, how do I type that? I mean, how do you type that tag? Well, you can learn about LaTeX. Okay. Now, if this is the only math class you will ever take, it's not worth the time nor the investment, to learn how to do this. But all of you are transferring to a 4-year university, which means you probably have plenty of opportunity where you need to type an answer that needs the mathematical notation. So for those of you who are curious and want to at least start to understand how these symbols are entered, you can do a right click, go to show math as, and then go to tech command. It is technically not TEX. This is technically tau epsilon chi, Greek characters, but you can call it text or you can call it tech either way. But if you click on that, it will show you the actual notation that you use in LaTeX to specify exactly that notation. So the first time you do this, the first few times it's going to be like confusing and you have a lot of stuff to memorize. But as you use it more and more often, it will just become second nature. I can type LaTeX without looking up anything for most of the math notation that I need to use. All right. So are there any questions up to this point about the concept of a set? Yes, go ahead.
I guess I'm just a little confused. 2.2 is in T is true. Is that just for example, or does T represent something?
Oh, that's just for example.
Okay.
It is, but it's based on the assumption of how T is
based
defined.
on that. Okay.
So it's referencing the same set T that I defined earlier.
Okay, cool. Thanks.
Yep. That's a good question, because it's on a separate paragraph, right? Yep.
So the discussion earlier about a set not having or only able to have unique elements.
Mm-hmm.
By comparing to a folder, there is a case where we can have the same file in nested folder. then in that case, is that still considered the same file, or is it because the file structure make it different file?
Because of the structure, they're different. So you're a little bit ahead of time, ahead of the class, because I will talk about how do you compare two sets. Yeah, because what you asked really has to do with, how do we compare two sets? In other words, how do we compare two folders? Do two folders contain the same files? That's basically what we need to get to.
Even if we have like nested set, it's still like put it.
You can use an example. I mean, if you want to use an example.
Yeah. Oh well, let's just say if set T have 12 in it, and then there's a set inside T that also have a 12. Does that work or?
Okay, that's a very good question because I can type that up. All right, so let's go ahead and type that up because that's a very good question. So this is reflecting, what you right?
Yeah.
So what Hugh is asking is reflecting not just an understanding of the material that we are currently dealing with, not only the definitions, but he is trying to explore. It's like, what if this is the scenario? So he's trying to look at the very extreme or scenarios that we have not visited, but may be possible. And then ask, okay, how do we apply these rules in those particular situations? So this is something that I encourage all of you to do. Okay, just take what we talk about in class to the extreme. Okay, think about your very extreme situations. It's like, oh, what about this case here? Okay, so let's go ahead and define a set S in this case, and we'll go ahead and say the set has A, B, as elements, and then it also has C in its own set as an element, and that's it. So now the question is, A in S is true, right? Because that's kind of obvious. D in S is false. That's kind of obvious too. Oops, it's typed. No, there we go. So I think these two are really kind of obvious because A is clearly just somewhere within the braces, and D does not appear anywhere. I mean, cannot possibly be in the set as in this case. So the tricky one is, what about C? So as it turns out, C in S is false. However, the set that contains C alone in S is true. In other words, the set, we call this a singleton set because it only has one single element, but the set of C that only contains C as an element itself is an element of S. But the element contained in the set here, it's the element C, the value C, is not technically a member of S because it is not immediate. It's not an immediate member.
Just for that, like my question more specifically is, can I have, like for that set, can I have A, B, a set of C, A? Can that be a case?
Let me try to capture what you said. Go ahead.
Like, it would be a set of A, B, and then just an element in there, which is a different set.
Like that?
No, I mean like for the nested set to have an element called
Oh,
A.
okay, I see. Okay, yes, so you can definitely have that too. So here you can have, that's perfectly okay.
Okay.
But in that case, then we can say the set of containing A, B as element in S is true. But so A itself, but this A in its own set in S that's false. Yep, that's right. Okay, so we are actually talking about something that is discussed a little bit later in the module, but these are good ways to think. I mean, if you have thought of these cases and you're just wondering, okay, how is it defined? Is it actually considered to be in but not in? That's a good sign that you are not only understanding containment itself, whether a particular element is in the set in the most normal form, but you're actually looking into the nested concept and go like, okay, what if it is nested? How is element of defined in that case? So those are, that's really good. All right. Any other questions before we proceed? Yep.
So then I reckon C is in set C would be true.
C is in set C is true. That is correct. So let me try to capture it. C in C is true. Yep, that is correct. All right. So let's move on. For some even more, in addition to this, what other weird set can we have? I'm not sure whether it's here or not. Okay, I'm just gonna be lazy. Nope, that's later. But when we get to empty sets, it's going to be fun too. All right, so section 3. So let's go through the food for thought, okay? Because that's kind of important. How would you implement the concept of a set in C or C++? If you know ahead of time a set is to only contain integer values, how would you implement a set? How do you check whether a value is an element of a set? How do you place elements into a set? So why do you think I would ask those questions? This is about implementation. It's not the abstract concept of a set. It is more like, okay, so here's a program. Your program needs to represent a set, and integers are the only thing that you can contain in a set. So let me give you some additional constraints. Let's just say that the integer values that you need to store in the set ranges from 0 to 31 only. Nothing outside of that range. So how would you implement that kind of set? Go ahead.
You make an array.
You can use an array. Okay, so
Use a loop to make sure that you give the limits.
mhm. So the problem or one of the issues of using an array, especially in C and C++, is you have to know how long the array is. So now the question is, how do you keep track of the length of the array? And you can, so there are really only two practical ways to do it. One is you pass along the length of the array when you pass the array, which is really just a pointer in C and C++. Or alternatively, there's a length property, but then that has to change depending on how many elements you have. So that it gets a little bit kind of tricky, especially in C or C and C++. So one way to do it is to use what we call a bitmap method. So that goes back to the representation of integers as base 2 numbers. How many people know that an integer is usually 32-bit wide or 64-bit wide? Some of you, okay? So that means each bit of an integer can be used to represent whether the corresponding value to that position is present, meaning it's a 1, or absent, which means it is a 0. So that's a very common way to implement a set when the values range that you need to represent is relatively small. Are we doing okay? So let's push that one more time, okay? And ask, but why do I need to understand that? I mean, C++ has a template library of set already. So why would I want to implement my own set using bitmap, and so on? Well, it's because the operating system is already using it. If you're talking about Linux or Mac OS X or Windows, part of the operating system understands the concept of set, and it's using a bitmap method to encode the containment of elements within a set. How many of you are kind of planning to transfer to CSU Sacramento, to Sac State? So at Sac State, there's a class called System Programming. which we used to offer here, but because of low enrollment, we just could not keep offering that class anymore. Every time we offer, the entire class would be Sac State students because they did not offer that class enough from Sac State, so they would actually take it from us over here. So there's a code that will let you monitor a bunch of files and basically say, if anything happens to any one of these files, let me know. Meanwhile, I'm going to go to sleep. Okay? And it's a very powerful type of programming because it allows you to track multiple files at the same time. And usually these are not actual files. They correspond to network connections. And we all know that network connections can be very slow. So most of the time, the program has nothing to do. But if anything happens to any of the network connection that the program is supposed to monitor, if it receives a byte or if this thing has cleared all the bytes that it's supposed to transmit, then we need to unlock the loop so that you can feed more stuff to the respective network connections. That particular system call makes use of the concept of a set, and the implementation is based on bitmap, which is what I described a little bit earlier. So even though this is a high-level concept, kind of abstract and mathematical, it is used in a low-level type of programming in this case. So I just want to bring awareness. There's no way I'm going to teach how to use the select system call, not in this class, but that is why it is relevant. All right, moving on to equivalence of sets. In other words, how can you tell if I give you a set S and I give you a set T, how can I determine whether they are the same or not? So the description says, let's say we're interested in whether set S and T are the same. The two are considered the same when every element in S is also in T, and every element in T is also in S. Well, that kind of makes sense, right? If this requirement is satisfied, then we say that those two sets are the same. Is that okay? All right, so let's go ahead and do some exercise just to see whether we understand whether two sets are the same or not. So now I define a set T, and we'll put BA, B, C, A in it. And now I'm asking S equals T is it true or is it false? Compared to the set S that we defined earlier here, and I now define the new set T down here, are they the same? They are the same, but tag, it's out of order. See, look at this thing here, AD is listed like this, and now we have BA here. It doesn't matter because it is a set, okay? There's no inherent order, which means we only care about are both A and B in this particular set? Yes, over here. Yes, over here. We're good. Okay, there's no need to look at the ordering of elements within a set. All right. So this is true. There we go. All right, so now let's move on. And this is where, where we kind of jumped ahead a little bit of time, is a set as an element of another set. In general, given two values x and y, knowing that x is a set, this is how we can determine whether x equals to y is true or not. In other words, this is how we compare two different sets. If y is not even a set, then we say x equals to y is false. That kind of makes sense, right? Because one is a set, the other one is not even a set. Yeah, type mismatch, okay, compiler error. If y is also a set, then we use the set comparison method in section 3 to determine whether x equals to y, so it goes back to the previous section. In other words, we ask, is everything in set x also in set y, and is everything in set y also in set x? Is that okay? Sort of? Now we can compare a set with anything for equality. It is not surprising that a set can be in an element of another set. Okay, we just explored that earlier. So in this case, if X is defined to be a set that contains A as a value, B as a value, and then the set of 1, 2, 3, the set itself is an element. Oh, wait, hold on a second here. The first question is, how many elements, if I were to ask the number of elements in X, what would be the answer?
3.
It would be 3, exactly, because we count the set of 1, 2, 3 as one single element from the perspective of set X. It's just like when you look at a folder, it contains a file, another file, and then a folder, and you ask how many items are in this folder. There are only 3 items because we don't care what is in the subfolder itself. Are we doing okay? Just imagine teaching this class before we have folders and that sort of concepts floating around. When I took set as a concept, that class did not use folders as an analogy. All right, so now we are moving on to section 5. I'm just looking at the time. When are we supposed to end?
420.
4:20? Okay, so we still got 10 more minutes, which is good. All right, so the notation of using the curly braces is great if you have a relatively small number of items to express as elements of a particular set. On the other hand, most of the time, we have to express membership that has an infinite number of members. In other words, let's try to look at a set of all the even numbers, even integers. They're like, wow, that's not just a lot of numbers, it's an infinite number of elements, right? So the question is, how do we do it? This notation here, seems to be intuitive, because you're basically showing examples of elements in a set, but it's not good enough, right? There's no way you can tell the next one, after -4, is it -6 or is it -8? Maybe. And then 2 and 4, and then the next one, maybe an 8, not 6. So it is not a very good and clear way to express membership. So in mathematics and also in computer science, the way we do that is something like this over here. So this bar here usually is called such that. Okay, when you see that bar within a set notation, it is basically such that. So E is a set, because we can still see the curly braces, but I'm no longer listing the individual items inside the set. Instead, I'm using the criteria that I'm going to use to qualify what belongs in this set and what does not belong in this set. So it reads as E is a set where an element X, where X is a value such that X is in Z. Now this symbol here means the set of all integers. And, how do we know this is and? Because we talked about it on Monday, right? So you might notice that I try to use symbols that was defined just in the previous class, like right away. So that means it's very, very important to get familiarized, or at least have a little lookup table in your notes, so you can look up those symbols really quickly. Okay. So and x mod 2 equals to 0. So that becomes a condition. Okay. If you just focus on this part here, it is specifying a condition. If there's a value x that makes this condition true, then it has to be in the set E, or in this particular set that we are defining. If it does not meet that condition, then it is not in the set. Are we doing okay? Yep, go ahead.
What does mod mean?
Mod means you are. Okay, so let me. I was just about to answer the question directly, which is against my principle. Okay. Do you know about the percent operator in C and C++? And what does that mean?
I don't know. I just
Okay.
remember.
All right. Okay. So the percent symbol should have been discussed in CISP440, and certainly in the 400 So by this time, we should know that symbol. So the percent symbol in C++ and also in C is what we call the mod operator. So the mod operator, if we are looking at x mod y, didn't we just use mod earlier in the spreadsheet? It's the remainder. So x mod y is the remainder of x divided by y. All right. It's a really useful operator. I mean, as much as it doesn't look like it is useful, it is actually very useful. So if x mod 2 equals to 0, all it is saying is x divided by 2 has a remainder of 0. Well, if x divided by y has a remainder of 0, what can you say about x in terms of odd versus even? It has to be even, right? Okay. So that's a notation that we can use in order to not to enumerate, in other words, not to list everything that is in the set. Instead, we define a criterion such that anything that meets the criterion is going to be a member, and everything that does not meet the criterion is not a member. Are we good so far? And somewhere along here, I use the phrase if and only if. Okay, so let's focus on the sentence that uses the phrase if and only if. There we go. This is the sentence that I want you guys to focus on at this point. So this notation literally says something x is an element of set E if and only if x is an element of the set of integers, which means x is an integer, and x divided by 2 has a remainder of 0. So the question now at this point is, does it really matter that I say if and only if? What if I say if? What if I say only if? Does it really matter? Yep.
Well, it's like if and only if with the and operator, right?
Yes, that's exactly the case. Yep. But why does it matter? And at this point, I'm going to point out a misnomer in the syntax of most programming languages. Yes, go ahead.
Is it so? It's like it's only exclusive criterion possible to qualify to be in set E.
Right. So so let's go ahead and explore what happens if it is just if, and what happens if it is just only if, because those two would not work. Okay, let's just say that this, instead of using if and only if, it's saying just if. Okay, so if you use if, that means whatever is right after if is a sufficient condition for whatever is before the if. Let me say that one more time. If I change the sentence so that it is blah, 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 if blah, 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 okay? That means if x is an integer and is divisible by 2, or if you divide it by 2, you have a remainder of 0, it is a sufficient condition to make x an element of E. So what that means is, yes, that guarantees all even numbers will now be in the set E. But what about something that is not even? I didn't say anything about that, right? So if you present me and say, what if x equals to 3? Now, most of you can say x being 3 means it is still an integer. Okay, that's good. But the remainder of 3 divided by 2 is 1, not 0. So it would have failed the condition, the condition that would be sufficient to say 3 is an element of E. But did it say anything about what if the condition is not satisfied? Nothing, right? So that means 3 can still be in E even though it is not it's not an even number. That's not what we want. So that means that's why if is not working. What about only if? if I change this sentence, so it becomes blah, 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 only if blah, blah, blah. Only if x is an integer and the remainder after it divides, the division by 2 is a 0. So I change it to only if. So when you use only if, it becomes the condition after the only if becomes a necessary condition for the other one. So in this case, it basically says, in order for something to be in E, it must be an even number to begin with. But it doesn't say anything about, but is it sufficient? No, it's just one of the many, many conditions that is needed. So that means I can look at 4 and say, is 4 an element of E? Can I determine from the sentence right here that 4 is an element of E? The answer is no. Because even though 4 is meeting the necessary condition, it doesn't say anything about, but are there any other conditions that are also necessary? We don't know. I didn't tell you. So there's no way to determine whether 4 is an element of E or not if I only use the word or the phrase only if. It is only when I use if and only if that you can say for sure 3 is not an element of E, but 4 is. So this is throwing a big wrench into your understanding of the conditional statement as expressed in most programming languages. So I'm going to give you an example on the whiteboard and say if x is greater than y, print f. Yes, I like print f. Percent d, comma, x, comma, y, semicolon. Okay? How you read the printf statement is not the issue. The issue is, what is this if saying? So because it's using just if, it is not using if and only if, right? So that means x is greater than y is a sufficient condition to print, x is actually greater than y, line feed. But what if x is not greater than y? What if they're the same? Technically speaking, this statement, by using just if, doesn't say anything about what if x is not greater than y. Because what we have just understood is we don't have a sufficient condition to execute a statement. But there may be other sufficient conditions where this statement should be printed as well. Are we kind of getting this or not? Maybe? Okay. So technically speaking, when you are dealing with a conditional statement without an else part, technically you really should say it is if and only if. Okay. Now you can tell this for those of you who are taking CISP440, you can present this point to Iraj and see his reaction. I think he's just going to go like, just stick with if. But for those of you in this class who are going like, but text says we really should be using if and only if, there's an easy fix, really, really easy. In C and C++, you just say define that. It's okay. I know most of you, probably have not ever seen the pound thing other than pound include, but pound define is one of the it's basically a macro expansion. It's telling the C preprocessor, CPP, every time it sees the string IFF, replace it with IF before the compiler gets to see it. So now you can actually use IFF as if it is a real keyword in your program to basically say, I feel comfortable now because what we really mean when we say if is really if and only if.
That's a great way to piss off your coworkers. Thank you. Very efficient.
Let me correct your use of the word if in the program. You have been using it wrong for the past 40 years. It's about time for you to retire. Ouch. Ouch. But it does matter, okay? Because in this case, if you use if, just if, it means 3 can still be in E, and it's still okay. If you use only if without the if, that means your 4 may not be in E. It is only if when you use if and only if that you guarantee that 4 is in E, but 3 is not. Okay? Yes, nuances, but important ones. Yes?
So if and only if doesn't need to be symbolized, it's just implied when we use this notation. Because.
Right. So okay. I know we are out of time in today's lecture, but I do want to show you, just a few lines down. So this notation, now P is what we call a predicate. In other words, it's really just a function that returns a Boolean. So this notation is exactly the same as this notation, which basically means this is just a condition to say whether X should be a member of E or not. But note how we use the double-sided arrow here instead of the single-sided arrow. This is if and only if, which means if this is false, this has to be false. If this is true, this has to be true, and also reverse the direction. If this is true, this has to be true. If this is false, this has to be false. All right. Okay, so we are running out of time. I'll let you guys go to enjoy your long weekend before we meet on Monday again. But you know what you need to do before Monday, right? Review all the material, gather the notes, change all the structure, put all the definitions at one place, get familiarized with all that stuff, and so on and so forth.
I just wanted to say, so I managed to email you today with all the info about the
Yeah,
the
I got
forms
it.
and the.
Yep.